In this section 1.3, we're going to be working with concepts mostly surrounding the idea of slope and some extensions of that to be able to work with some linear functions and linear equations a little bit. So to begin with right here, we want to be able to look at relations that we classify as being linear themselves, and then also relationships that are nonlinear. So it's very clear, of course, when you look at the graphs that the relationship that is on the left-hand side is what we would classify as being linear because it's a line, and then this relationship is not a straight line. Okay, so we could say for sure it's nonlinear. There's a more specific thing that we can call that type of function, but obviously it's not a line, so we'll just call it nonlinear for right now. And the biggest thing that we can see to distinguish between linear functions and nonlinear functions is how the position on the graph is changing over time. So if you look at like the linear function and you look at just different points that are on the graph, you'll see that the ratio of the rise to the run is always the same, and that it goes down -2 and then over 1 and then down 2 over 1, right? But then if you look at like the nonlinear function and you look at some points that are on the graph, you can see that it goes up 1 and then over 1, but then it's going to go up 2 and then over 1. And so there's a difference in terms of what we're seeing slope-wise right there. And so ultimately, to distinguish between the two of them, in a linear relation, you're always going to be able to see a rate of change that remains constant throughout the entire duration of that relation. And then in a nonlinear relation, you'll see that the rate of change ultimately changes, right? So there's going to be at some point in time where, the slope between any 2 points is going to be different than any other 2 points, right? All right, so with that then, let's go ahead and actually talk about slope a little bit more formally here, okay? So we're going to really try to contextualize the idea of slope right here. And so obviously one way in which slopes are talked about is like in ski slopes and slopes of mountains and that sort of thing, right? And so when we talk about these slopes, one big thing that is really important for us is to talk about the steepness of these slopes. And ultimately what's going to make something steeper is if you have this amount of rise between two different points, but like this has this much run and this has this much run. There's a very big difference there in terms of the steepness that you're going to have, right? And so it would turn out that this right here is going to be obviously a steeper slope. And the reason why that would be is if we actually put some numbers on here and say that like this was 5 and 5, but this was longer, like 15, and this right here was like 8, then the ratio of the rise to the run and then the rise to the run would be that this number right here is a bigger number because 5/8 would be like 0.625, but 5/15 would be 0.3 repeating, right? So because of the larger magnitude of that ratio of rise to run, we get something that's steeper, right? And that ratio of rise to run is actually what we define as being slope, right? So just giving some kind of key characteristics of slope here. When we define slope, it is a ratio. And so what a ratio means is just a division of two quantities, so a fraction, right? And it's the ratio of the um, change vertically, which we usually denote as the rise, to the amount of change in position horizontally, which we usually denote as the run, for some surface, right? And so some ways in which we'll look at this then is talk about it as being like the change vertically divided by the change horizontally, which is equivalent to the ratio of the rise to the run. Okay. But as we'll see in a little bit, this definitely has a lot to do with y coordinates and x coordinates and things when we start looking at graphs of different relationships. But before we do so, let's talk about an actual application right here. So you can see that to be able to comply with the American with Disabilities Act requirements, wheelchair ramps must have a maximum slope of 1 to 12. Suppose the porch is 20 inches above ground level, then how far along the ground must the ramp be constructed? Okay, so we know that this has to hold for any ramp to comply with the ADA, right? It has to have a maximum, so highest slope of 1 to 12. So when we have slope, slope is always the ratio of the rise to the run. So for every 1 unit of rise, there should be 12 units of run. So it should look like, something like this. For 1 unit of rise, there's going to be 12 units of run, right? And then what we know about this particular porch is that it's 20 inches above ground level. So this distance right there is going to be 20 inches high. We want to know how far out into the grass area there that we should construct that ramp, right? And so this 20 inches should correspond to the 1 unit of rise, right? So for every 1 unit of rise, there should be 12 inches of run. So since we have 20 inches of rise, then the amount of run we should have should be 20 times 12, which would be 240 inches, right? And so we would at least need to make it be constructed out to 240 inches and then or more, because if you go out farther into the grass, it'll just make it shallower. So and that's okay. We're trying to avoid it being, too steep, right? And then at the bottom right there, it's just kind of a second part, a little different question that says that a ramp is 18 feet long and 16 inches high. Does it meet the ADA slope requirements? So if we have a ramp that's 18 feet long and then 16 inches high, it would look something like this then, right? Now, then to be able to find the actual slope here, we would need to divide the rise and the run in this order, okay? But then because the units are different, you're going to need to convert one of them to the other unit, so if the units are the same. So probably the easiest way to do so is to change the 18 feet into inches, because you just got to multiply 18 by 12 then. So that's going to lead you to, I believe, 216 inches. Yep. And then you'd be able to hopefully reduce that fraction. I think we can divide by 8, get 2, and that should be divisible by 8. Yeah, because then that would be 27. So you get a ratio of 2 over 27. And then that 2 over 27 ratio, you need to compare to 1 over 12 to see if it's going to be legal, right? So 1 over 12 is going to be 0.083 repeating, and then 2 over 27 is going to be 0.074. Okay, so we know that the maximum slope has to be 1 to 12. So this right here is supposed to be the maximum. So if we go over that, it would be illegal. And you can see that this right here is falling under. So therefore, that particular ramp would meet the requirements. It would be legal by the Americans with Disabilities Act. Okay. Some other applications in which we can see slope as well exist in grade of roads. So you may have been driving in mountainous areas and stuff where you see the road signs that say like 8% grade or whatever it might be, right? And that's really actually just expressing the steepness of a slope, because all that grade is slope. Okay, so grade of a road is rise over run, but we just express it as a percent. So like when we were just talking about the previous ADA problem where the maximum slope of a ramp is supposed to be 1 over 12, right? We just saw that this is what the slope would be. Okay, but then if you just turn that into percent form, in this case it would be 8.3%, then this would be what the grade is. Okay, so the grade is just the percent form of the decimal. Okay. So I want to go to this problem right here because we don't really have a lot of information in that first problem to go off of. But in the second problem down here, for a half-block stretch of Filbert Street in San Francisco, the road has a 31.5% grade. We wanted to determine what the run of this stretch would be if it rises 65 feet, right? So you have a half-block stretch of the road that goes downhill or uphill, depending on which direction you drive up it, right? And we know that it rises 65 feet. So right here, this is a 65-foot rise, but we don't know the run, and we want to be able to try to figure that out, right? Now, what we also know is that the road has a 31.5% grade. So if you put that into its decimal form, so move the decimal over a couple of spots, this would be equivalent to a slope of 0.315, right? And so what we know about that 0.315 is that should come from the rise divided by the run. We know that 65 is going to be the rise here, and then the run is x. So 65 divided by x should be able to equal 0.315. And then you just need to solve that equation to be able to find x then. So if you multiplied by x, it would cancel out the x on the bottom of the fraction there, and then you'd have to multiply to the other side and bring x over there. And then you could divide by 0.315 and you'll get x alone. So really, right there, 65 divided by 0.315 would be what you'd need to evaluate in your calculator. And then that comes out to be that x is about 206.35 feet or so for a run of that stretching run. Okay. All right, so let's talk about slope in terms of a graph right here. So if we have some sort of like a line that's going through your graph, so let's say that we have this line right here, and we want to try to be able to determine the slope of the graph. What we would need to do is we need to be able to find like 2 points that are going to be on the line, and then determine the amount of rise that's happening between those two different points, and then also determine the amount of run that is happening between those two particular points, right? And that would ultimately be your slope. So we know that slope is always going to be equal to the ratio of the amount of rise divided by the amount of run. Okay. But if those two black dots had coordinates that we actually knew, so like we knew this x coordinate and this y coordinate, and we knew this x coordinate and this y coordinate, and then to specify the difference between those xy coordinates, we could call one of them x1, y1, and then call the other one x2, y2, right? Then it would turn out that this distance right here, this run, would really correspond to the difference between this coordinate right here and this coordinate right here, which would really be the difference between x2 and x1. So it would turn out that the run would actually be x2 minus x1, the bigger x minus the smaller x, right? And then also similarly, we could figure out this distance, the rise right there, if we were able to subtract this y coordinate and this y coordinate together. And that would correspond to y2 and y1. So it would turn out that the rise is going to be y2 minus y1. So equivalently then, the rise is actually going to be y2 minus y1, or in other words, the change between those two y coordinates, and then on the bottom here, the change in these two x coordinates. So for any 2 points that are on a line, right, that's always how we can calculate and compute slope, and gives us that slope formula that we can use, okay? So we're going to look at some examples of using the slope formula in just a little bit. Just know that there's really four main types of slope that we should be aware of. So whenever you have a line that when from left to right is going like up a hill, like you see this penguin is going up the hill, we always classify that slope as having a positive slope. And in fact, when you find the slope number, the slope will always be a positive number. And then right here, when from left to right on the graph, it's going downwards. That's always going to be a negative slope, and indeed the number for the slope will be a negative number as well. In the third one right there, you can see that the penguin is just going flat. That is always classified as having a zero slope, and indeed the slope right there is actually going to be the number 0. And then the last one, the penguin looks like it's going to die, right? That is the only slope that doesn't actually have a number associated with it. It's a slope that is undefined, and we'll talk about what that means and what that is in just a little bit, okay? All right, so let's look at some examples where we could find some slope from graphs and that sort of thing. So one thing we want to concern ourselves with is knowing whether which points on the line we need to use to find the slope. Like, does it really matter? So if I were to like pick, say, this point and this point right here, and then find the rise, um, when I move from this point to this point, I'm moving in a negative direction. So I can't just say that that's 3 right there. I'd have to say this is -3. And then if I continue going this way, that's a positive direction. When we move to the right, then that's going to be 2. And so we would end up getting then like a slope of -3/2, right? But if you were to pick a couple other points on your graph, like let's say you picked this point and then this point down here, you could see that if we went the other direction, so we started at the rightmost point and went up this far, we would go up 6, so that'd be +6. But then moving in this direction, we would get -4, because going to the left is negative. And so you would get your slope to be +6 over -4, but that's going to still reduce to be -3/2, right? So it does not matter which points on the line you use to find its slope, right? So you can use any points. And then because I changed the order in terms of starting at the left point and working to the right point, or starting at a right point and going to a left point, it doesn't matter which point is going to be x1, y1, x2, and y2 either. So for that, it also doesn't. Okay. So here we want to be able to just find slope of a line that passes through two given points and then also be able to classify the slope. So if we have a line that's going through these two different points, we can just use the slope formula of y2 minus y1 over x2 minus x1. So if we were to do y2 minus y1, we would want to subtract these couple of numbers because they're the y coordinates, and then evaluate 10, 0, and subtract it. And then for the other part, we'd have to do x minus x and subtract in the same direction that I subtracted from 10 to 0. So I'm going to have to subtract 4 and negative 2. Now, when I do this part, when I have the numbers 4 and negative 2, we're going to need to subtract. So hence the 4 minus negative 2 on bottom is actually going to turn to plus, right? So we get 10 over 6, and then that's going to reduce to 5/3. That would indeed be the slope between the two lines. We are asked to classify the slope as well, which is to tell what type of slope this would be. This would end up being a positive slope based on those four classifications that I gave you earlier. And that's because 5/3 is a positive number, and so we would have that slope happening. Okay. With this example right here, if you were to do y minus y, you would have -1 minus -1. And then for the run, you would have 2 minus -3. And so then you'd end up with -1 plus 1 over 2 plus 3, which would be 0 over 5. And then if 0 is in the numerator, you have 0 out of 5. That really just means that you have 0. And so that would be your slope. And then you can classify that slope as being a 0 slope. What that really means is you just have a horizontal line, because if you were to look in a graph and you were to plot the point -3, -1, and then plot the point 2, -1, they'd be approximately in those locations, which then would have a horizontal line connecting those 2 points. Okay. For this one right here, you'd have 7 minus 1, and then x minus x would be -6 minus -4, which would result in 6, and then -6 plus 4, which is 6 over -2, and then you could reduce that even to -3, right? So this ends up being a negative slope that we can classify that as. And then the last example right here is a pretty special case, because when you do the y minus y, -4 minus a +2, and then x minus x, 5 minus 5, you're going to get -6 over 0. Okay, anytime 0 is on the bottom of a fraction, that means that we actually aren't getting an answer right here, because you can't divide by 0. So in this case, you would need to say that the slope is undefined. Okay, so don't say that that is the slope, because that is not the slope. It's not even a number. So what the slope actually is undefined. So I'm going to highlight in green right there that that's what the slope was, similar to right here in green, and right there in green, right there in green. That's what the slopes all were. Okay, and then what I highlighted in yellow right there was the type of the slope in each case. And then for the very last one, the fact that it's undefined is also its type as well. Okay. All right, when you're finding slopes from graphs, you can also use the slope formula, just what we just did, as long as you find the coordinates of 2 points that are on the line, but it's probably just easiest to like count squares and such as you're finding slope. So if we were to try to find the slope of segment DC right here, or line DC, you'd be finding the slope of this right here. And so if you started at D, you'd want to find the rise first, the vertical amount of distance, which would end up being 1. And then if you're moving to the right, that's also going to be positive, and you would count 6 grid squares right there. So the slope for that line would end up being 1 over 6. For line AC, if you started at point A and you worked your way down to point C, you'd want to work down first 1, 2, 3, 4, 5 units. And because you're going down, you want to specify that as being a -5. And then you're going to go to the right 6 units, and then end up getting a slope there of -5/6. Okay. The other two should be a little bit more straightforward, because for line AB is just going straight horizontal, and that's always going to be just the number 0 for its slope. And then for the very last one, we have AD, and that's what this line is. Anytime it's straight up and down and vertical, those are the types of lines that always have an undefined slope. Okay, just some other things that you want to think about in terms of finding slope from a graph. So like if you look at the very first example over here, we want to find the slope of the line. So if we found a couple of points on the graph, you could see like right here and right here would be a couple of nice points that we could use to find the slope. And when you go down this far, it seems like you go down 1 and then over 2 and then say, okay, well, then the slope is -1/2. But it turns out to not be the correct answer because when you look at the scaling of the graphs, this is at 24 and this is at 21. So in actuality, you're actually going down -3, right? And then also the x scale goes from 4 to 8. So you're actually going over 4. So that wouldn't be the correct slope. The correct slope would actually be -3/4. So just pay really good close attention to the scale of your graph because, you know, graphs aren't always going to come by ones. They might come by 4s or 20s or whatever, right? All right, we'll skip past over that and then jump to here. So here we want to be able to find the slope of a line that passes through these points. So we'd be able to use slope formula. The biggest thing here is just understanding how we can do this with like fractions, right? So nothing's really going to change in terms of using slope formula because we should just be able to take y minus y and then also be able to take x minus x and then just be able to simplify, okay? So in the top of our fraction, what I have in the red color right there, we're trying to subtract the fractions. And whenever we're trying to subtract fractions, we know that we need common denominators, right? We actually have the common denominators right there because the denominators are 3 right there. So when we simplify, then we'll just be able to get -5/3 by subtracting those couple of fractions, right? Now, in the bottom part, however, we don't have common denominators. And in fact, we actually only have one of them that's actually expressed as a fraction, just that -3/4. So we'd want to turn the 3 into a fraction that would also have a denominator of 4. So you'd want to multiply that by 4/4 then. Hence, we would have 12/4. And then because of the subtracting a negative, we would need to add 3/4. And therefore, we're going to get -5/3 in the numerator still, and then now 15/4 in the denominator. Okay? This is not considered simplified because we have two separate fractions, like within a fraction itself, and we don't ever allow fractions to be just left in fractions. It's not simplified. So whenever we are doing a fraction, and divided by a fraction, we know that that is equivalent to multiplying by a reciprocal. So this would be the same thing as taking -5/3 and multiplying it by 4/15 then. And then we'd be able to just multiply across via multiplication of fractions and get -20/45. Okay, so that would be the slope, and then that would be a fraction to be able to reduce. Both the numerator and denominator are divisible by 5. So -20 divided by 5 is -4, and 45 divided by 5 is 9. And so that would give you your answer there of -4/9. Okay. The example below would be pretty much the same. I'll work through that and post that in the notes a little bit later on. All right, and let's look at some problems here. So now we have a line with slope 3 that passes through -2, 7, and r -11, and we want to determine what the value of r would be. So we know that the slope is supposed to come out to be 3, right? And the line passes through these couple points. So if I were to take these points right here and I were to find the slope, it should come out to be 3, right? And if we find the slope, we would just need to be able to take y minus y, so -11 minus +7, over x minus x, so r minus -2, and then it should come out to be an answer of 3, right? And so from that, then, we'd want to be able to try to solve to find what the coordinates of r would need to be. On top of the fraction, we can combine the -11 and -7 to give us -18. And then the bottom is r plus 2 equals 3. So what you'd be able to do is like clear out the denominator of this. And so you'd be able to multiply by the quantity r plus 2. And then you need to, in parentheses, multiply the other side by r plus 2, because then that 3 would be able to distribute. So you would get 3r plus 6 on the right-hand side there. On the other side, the r plus 2's would cancel out, and so just -18 would equal 3r plus 6. And so then just subtract the 6 and divide by 3, and you'll end up getting -8 is going to be what that value of r is. Okay, so in other words, -2, 7, and then Now we know -8, -11. Those would be the 2 points on the line that then would have a slope of -3 between the two of them. Okay. Similarly, I will work through the example right below, but it's pretty much similar to the example that you just saw there. In terms of finding slope from a table, so if we know these tables are linear in nature, so in other words, the xy points when plotted will all fit perfectly on a line, then it's pretty easy to be able to find a slope. So if I look at the very first table right here, we know that in lines there should be a constant rate of change. And so if I look at the change in my x coordinates, you can see that each time we're just adding 1. And then if I look at the corresponding change in my y coordinates, you'll figure out that there's a change in 5 every time. And so because of that, the change in y over the change in x each time is always +5 over +1, which is 5. And so that would actually be the slope of the line in that particular table that you're seeing right there. Okay. Even in like this example right here, where if you see that it's going +4 and then +2 and then +6 and then +7, okay, there's like different gaps between the x's, right? But if you find the change in the y as well, where you're subtracting 4 there, and then here you're subtracting 2, here you're subtracting 6, and here you're subtracting 7, and then you find the ratio of the rise over the run, so make sure you always put the change in the y on top. You would find that actually all of these ratios right here are actually all going to be equal to each other, right? And so when those ratios are all equal, you know you actually have a line. And so in this case, the slope would actually be -1, because that's what all of those fractions are going to be able to reduce to, right? All right, and we'll skip past that. Okay, and then just average rate of change. If you had like a relationship like this right here, and let's say like this is your function, right? You could describe some sort of a rate of change between, say, this point right here and this point right here in terms of describing a slope. So when you find a slope between those couple of points, you're really trying to find the slope of that particular line. And so we just describe it as an average rate of change because it's not the exact rate of change. Because it turns out that because the graph is curved and stuff, the rate of change is changing all the time. So this is what we refer to as just like an average rate of change, right? Telling us what's averaging over time. So if we were to see like this example right here, we want to find the average rate of change in the diameter of the tree between 1980 and 2020, right? We're just finding an average. We don't know necessarily, that the rate of change in 1985 was the same as in 1992 or whatever, right? It was always changing. And so you can see that the diameter in 1980 was 137 inches and the diameter is 141. So we probably just want to specify like in inches per year, right? What the rate of change would be. So it'd probably be appropriate to just take 141 and 137 and subtract them and figure out that there was a 4-inch change between all those years. And then also subtract the years of 2020 and 1980 and then get that it changed 4 inches in 40 years time. And then if you reduce the fraction 4 over 40, it reduces to 1/10, which is equivalent to 0.1. So 0.1 inches per year would be the average rate of change, right? Doesn't mean it changed 0.1 inch every year. One year might have changed 0.08, next year might have changed 0.2, whatever, right? Cool. Then I'm going to skip over a little bit more stuff here so that we can get to now graphs of lines in slope-intercept form, okay? So slope-intercept form is something that you should be familiar with because it's just y equals mx plus b. And this is actually getting to the equation of a line. So I want to take just a little bit of time right here to derive where slope-intercept form is actually coming from. So if we had on our graph of the line right here some point that was xy, just any arbitrary point. And then we also happen to know the point that is on the y-axis. So we know the y-intercept. We know that the x-coordinate has to be 0, right? Because it's a y-intercept. And then let's call the y-intercept number b. Okay? So what we would be able to do is we would be able to find the slope of a line based on our slope formula. Of a line going through any point x, y on the line, and then the y-intercept in particular, because you would be able to take and subtract y minus y, and then also be able to subtract x minus x, and then that should equal the slope m of the line, right? Well, then putting this a little bit more simply, x minus 0 on the bottom is just x, okay? So then y minus b divided by x equals m. Now what I'm going to do is I'm just going to try to solve for y and get y alone so that we get, y equals mx plus b. So you would just need to multiply this side by x and then multiply this side by x. And then you'd be able to have that y minus b is equal to m times x. And then you can add b to both sides so that y is going to be equal to x plus b. Right. So that's ultimately where slope-intercept form is coming from. So what we should know about this, of course, is that the b number is really specified where the y-intercept is, so where the line is crossing through the y-axis at. And then we should also know that m is specifying what the slope is for your line, right? Okay, so a couple questions that you'll see right here. Looking at the first one, we're asked to find the slope and to find the y-intercept of the graph of the equation y equals 10 minus 0.83x. This is actually y equals b plus mx form, so it's in slope-intercept form. So what that means is this 10, the number that's not with x, is going to be the y-intercept. So the y-intercept, make sure you express it as a point, of course, is 0, 10 then. And then what the slope is going to be right here is it's going to be negative 0.83. And that would be the ratio of the rise to the run. Okay. For this other equation right here, you have 3x minus 6y plus 10 is equal to 0. And if you want to find the slope and the y-intercept only, those are two things that you could get from slope-intercept form. And so you would need to just take this equation right here and solve it to get the y term alone. So if I were to, let's say, eliminate the x term and the 10 from this side, I'd have to do the same thing to the other side of the equation to keep it balanced. We would end up then getting negative 6y alone, and that's going to equal negative 3x minus 10. And then we need to undo the multiplication by negative 6 by dividing by negative 6 to get the y alone. And then divide that other side by negative 6 as well. When you do negative 3 divided by negative 6, you're going to get a positive 1/2. And then when you do negative 10 divided by negative 6, you're going to get a positive 5/3. So this would be what your equation is in y equals mx plus b form. And then know from that that the slope has to be 1/2. And then the y-intercept location is going to be at the ordered pair 0, 5/3. In terms of graphing lines now, we're going to look at a few slides of just being able to graph lines. All 6 of these equations right here that you see are all just y alone equals like a number times x, right? So in the very first case, you have just y is equal to x, which really means that all of the ordered pairs where y and x are the same number should be true. Now, if you think about this in terms of y equals mx plus b form, all of these are really going to have plus 0. Which means that when you start your line then, you're going to start every single line on the y-axis at 0, which means all of these lines are going to be able to cross to the origin, okay? So with the very first line, because there's a 1 in front of x, you would just need to draw a line that has a slope of 1. So this equation right here is going to be the equation for y equals x then. Okay. And then for the second one that'll have an orange right there, it's y equals 2x. So you would just need to make sure that you go up 2 and over 1 like this. And so this orange equation with a positive slope would be what y equals 2x is going to end up looking like. And then in the case of the next example, where you have negative 1/3 x, just make sure that you have a negative slope and that you'll go down 1 and over 3, down 1 over 3, down 1 over 3, just like this. And when you connect all of those points, that's going to give you the equation for y equals negative 1/3 x. Okay. So all the other examples here are going to be pretty much the same and similar, of course. All right, when you look at examples here, this is actually going to have both the m and the b involved. So with this equation right here, this is in y equals mx plus b form. What you need to identify, first of all, is this number that's not with the x, because that's where you're going to start your line. This is going to be the y-intercept of your line. So on the y-axis, this axis, you'll be able to start the line at 1, and then be able to use the slope of negative 2 over 3. So if you go down 2 and then over 3, down 2 over 3, down 2 over 3, you'll be able to get a lot of different points that you can then connect, form a line, draw your arrows, and then you're done, right? With like the next example right here, you'll see that negative 7 would be the y-intercept. So you'll need to start the line down here. And then it has a slope of 5. You'll need to think about 5 as equaling 5 over 1. So you'll rise 5 and go over 1, rise 5, go over 1. So just like that would give you what that equation is going to look like. And the last example is a little interesting. So with this one right here, it turns out that this is going to be your y-intercept because that's the number that is not with the x. Now 3/2 actually ends up being like 1.5. So yes, at 1.5, you'll want to start the line right there between 1 and 2. And then you'll see that this right here is going to be the slope of your line, which is 0.8. Now, you should be able to turn that into a fraction because you know that 0.8 is going to be equivalent to 4/5, right? So then you can use that as a rise of 4 and a run of 5. So you will start at that blue dot, and if you go up 1, 2, 3, 4, and then over 1, 2, 3, 4, 5, that's where you're going to land. So yeah, it's like, between 5 and 6 y-wise, and then right on 5 x-wise. But that's totally okay, right? Obviously, you can find more points and such, but there's your line. And then for a very last example, before we look at some special cases and such here, is the graph of y equals negative 13/4. You see that there's not actually an x variable in this equation. It's just y is equal to really 0 times x minus 13/4. And so you can see it actually in being y equals mx plus b form. So what this really means then is that actually your y-intercept is going to be at negative 13/4, which as a decimal is going to be negative 3.25. So right there. But then it does have a slope of 0, which means it goes horizontally. So it turns out that actually you need an entire horizontal line to satisfy this equation. So this equation right here is not just a point, it's actually a line because every single point on this line, like this point right here of negative 6.5, has a y-coordinate of negative 13/4, right? So we're just trying to reflect all of the solutions, all of the points that have y-coordinates of negative 13/4 there. Okay, so with that, that's a good segue into talking about horizontal and vertical lines. So when we talk about horizontal lines are always going to go straight left and right, and then vertical lines are always going to go straight up and down. And so what we'll see happen in horizontal lines, if this point right here is say like negative 3, 5, and then this point right here has like an x-coordinate of 6, it also has to have a y-coordinate of 5 as well. So we're going to see that the y-coordinates are all the same. So whenever you have a horizontal line, y equals whatever that number is that it's at height-wise is always the equation. So it's just y equals the number. There's no x in the equation, okay? For vertical lines, if this right here was say negative 4, 4, and then this point right here was like negative 4, negative 1, you'll notice that actually all of the x coordinates are going to be the same for any vertical lines. And so because of that, x equals a number is always an equation for a vertical line. Okay, so let's see how that pans out right here. So if we were to look at, say, this line right here, line A that's in the red, and we want to write an equation for that line, because it's just a horizontal line, then if you see that it's going through 6, that's going to be the equation y equals 6. Because really it is y equals 0x, has 0 slope, and then a 6 y-intercept. But you don't want to write it like that. Write it more simply as just as y equals 6, right? And then for the second line that you're seeing right here, this is a vertical line. And so if you look at the x-intercept, it's right there at negative 4. This would be the equation just x only is equal to negative 4. Okay. Now the other two lines are all diagonal lines, so those are going to be equations that you can actually write in mx plus b form. So for this line that you're seeing right here, for line C, you can see that its y-intercept is actually at 0. But then if you look at the slope, it seems to be going up 1 and over 4. So the equation would be that y is equal to 1/4 times x and then plus 0. But of course, plus 0 isn't really going to do anything, so you don't need to write it. So it ends up being just y equals 1/4 times x. Okay? And then the very last equation that we have for D is going through negative 3 for a y-intercept. And then it seems that it's going down 3 over 3. So actually down 3 over 3 would simplify to just a negative 1 slope. So y equals negative x, negative 1 times x, and then because it was going through negative 3 for y-intercept, minus 3, that would be the equation for that orange line that you're seeing. All right, so then just some last ideas just to kind of close things up right here. In terms of talking about linear versus non-linear relationships. So if you remember at the very beginning, I showed you a line and then something that was not a line, and we talked about how a line is always going to have a constant rate of change, and then something that's not a line is not going to have a constant rate of change. And so when we're asked to determine whether something's linear or non-linear, you should really anchor yourself on finding a constant rate of change if that's happening. So to know if this table right here is linear, we'd really want to determine if like -2, 7, -1, 4, etc., when plotted, are all going to be together on the same line as one another. So we could do so by checking the slope between all of the different points. So like right here, if it goes up 1 in x and then down 3 in y, we would know that the slope there is going to be -3/1, which is -3. We hope that's the case all the way throughout. And indeed, this is -3, -3, and then this is +1, +1, +1. So we're going to get the same ratios all the way throughout. So therefore, this relationship is going to be linear right here. And the reason why we know that and how to justify that is because there is a constant rate of change of -3 all the way throughout the duration of that particular table. Okay. If we look at some of the other tables, the change in the x's here are all +1, +1. And then this right here is -3, and then -1, and +1, and +3. So if you do -3/1, and then -1/1, and then +1/1, and 3/1, those fractions are not all the same, which means that the rate of change is changing. So this table in the middle right here is going to be non-linear, and your justification would be just that the rate of change was not constant, right? The rate of change was changing. And then the very last example, in the x's, you're going +4, +2, +12, and then the y's, it's going +2, +1, and then +6. And then if you do the change in y over the change in x for each of these, you'll see that actually all of the fractions all reduce to 1/2, so they're all the same actually. So therefore this last one is actually going to be linear because it has the same rate of change all the way throughout the duration of the table, of course, right? Okay. Just to give you a little flavor of examples of equations that are linear versus ones that are non-linear. Anytime you have an equation like y equals 4x plus 3, right, and x plus b, or if it's just y equals a number like y equals 5, or x equals a number, so it's a vertical line like x equals -8, those are all linear equations. Now, we can also look at like if you had 5x plus 4y is equal to 7, where x and y are on the same side, you can ultimately like solve it to get it into a form like the first one, y equals mx plus b. So that would also be something that we would recognize as linear equation, right? So those are common things that we should recognize as being graphs of lines. We should also recognize things that are not going to be linear equations. So if you have something like y equals 3x squared plus 4x minus 5, that is going to be non-linear. And the reason why that is right there is because you have an exponent on the x. So just be careful about that aspect right there. If you put x into some sort of like a radical, like a square root or something like that, in this case I put a cube root, that's also not going to be linear. If you also put the variable into like absolute value bars or something like that, also not going to work. And if you also put the variable into an exponent, like y equals 2 to the x, that's also not going to be a linear equation. So the graphs of all these things we'll study later on. Just know that those are some of the more common things you should recognize for right now as being things that are not graphs of lines. Okay? All right, so we are asked here to determine whether each graph represents a linear relation or a nonlinear relation. So in the first example right here, this is definitely a linear relation because it's a straight line, right? This turns out to be a nonlinear relation because it's not a straight line. It has straight components to it, but ultimately the whole thing is not a straight line. So it's definitely nonlinear. There's a second question right here that asks if each of these is a linear function. So we said this first one right here was linear because it is. But to be a function means that it needs to pass the vertical line test, right? And if I draw a vertical line right here, it actually hits the graph at every point, which means it fails the vertical line test. So this right here is a linear relation, but it is not a linear function, right? And then, of course, because that right there was non-linear, It's not a linear function, but at least this is a function in the second graph, though, right? It passes the vertical line test, so therefore we can say it's not just a nonlinear relation; it's actually a nonlinear function in that particular case, right? Okay, so the big things that you should take away here, of course, today is understanding slope and all the different things about slope that we worked with earlier. And then down at the bottom right there is just a little summary of graphs of lines of different types of linear functions and such too that can be helpful reference for you.